Hello friends, in this video I'd like to solve the following problem from the Japanese Mathematical Olympiad, final round 1992, problem number 3. We wish to prove the following inequality. Sum from k equals 1 to up to n minus 1 of n over n minus k times 2 to the power k minus 1 is strictly less than 4 for every integer n which is greater than or equal to. So my hints for this problem: first, this sum can be simplified a little bit by changing k to n minus k. Also remember to check the boundaries of summation. And then this inequality is pretty easy to be demonstrated by mathematical induction. So give this problem a try and I will see you in a minute. Okay, so I hope that you tried to solve it. My proof will go like that. Let's take our sum, and I will write the boundaries of summation as k is strictly greater than 0 and strictly less than 1. It's another way of stating the same boundary of summation. Okay. And now, what will I do? Now, instead of k, I will put n minus k. So n minus k is greater than 0, less than n. N stays the same, and here I have n minus k to the power 2 to the power n minus k minus 1. Okay. And now let's simplify our sum a little bit. So it's a sum for 2 sigma. Okay. Our sum, if you solve these inequalities, it's k goes from 0 to n again, n over k times 2 to the power n minus k minus 1. And finally, let's write it as k goes from 1 up to n minus 1 of, well, let's take n over 2 to the power n minus 1 in front of our sum, because we are summing over k. And here we have 2 to the power minus k in the denominator, so it's the same as 2 to the power of k over k. And we wish to prove that it is less than equal 4. In other words, this inequality, which we wish to show, is equivalent to saying that our sum as k goes from 1 to n minus 1, 2 to the power of k over k, is less than 2 to the power n plus 1 over n for every integer greater than equal to. We wish to prove that. And now we will do it exactly by induction. Mathematical induction. And also, one more step, I will sum for brevity's sake, I will say that this is s of n. Okay, now I will check the first two cases. So let's look at s of 1, s of 2, and s of 3. Well, s of 2 is the sum which goes from 1 to 1 of 2 to the power of k over k. It's just 1. And this is strictly less than 2 to the power 2 plus 1 over 2, because it's 4. Okay, what is f of 3? s of 3, sorry. S of 3 is 2 plus, if we put k equals 2, we will get 2, so it's 4. Okay, and is it less than 2 to the power 3 plus 1 over 3? Well, it is, because here we have 16 over 3. 16 over 3 is greater than 4, so it's good. And now let's assume that s of n is less than 2 to the power n plus 1 over n for some integer n greater than or equal 3. And now let's look at s of n plus 1. S of n plus 1 is the sum which goes from 1 to n, 2 to the power of k over k. And now this is exactly the same as s of n plus the last term, 2 to the power of n over n. By our hypothesis, s of n is less than 2 to the power n plus 1 over n. And that is, after simplification, 3 times 2 to the power of n over n. And now it would be sufficient, it will be sufficient to show that this number is less than or equal 2 to the power n plus 2 over n plus 1 to close our induction. I need only weak inequality because I already have strict inequality in this place. So it suffices for this inequality to be weak. Okay, and now is it true? Yes, it is, because this inequality is, in reality, it's equivalent to saying that 3 times n plus 1, 2 to the power of n, is less than or equal 4 times n times 2 to the power of n, and that in turn is equivalent to saying that 3n plus 3 is less than or equal 4n, and that is equivalent to saying that 3 is less than or equal n. And by the way, it's our assumption that n is greater than or equal 3. That's because I have considered first two cases separately. For this argument to work, we need n to be greater than or equal 3. And it is. It is. So in other words, that implies that... Sorry, I'm running out of space. That implies that f of s of n plus 1 is less than 2 to the power n plus 2 over 2 to the power over n plus 1, n plus 1. And that closes our induction, because we have checked first two cases separately, and now we have made our induction step. And that means that our inequality is in fact true for every integer n greater than or equal to. And that's it. So thank you for watching, and I will see you next time. Goodbye.